integration by parts. Okay, so this is the rule to undo product rule. And so I call it informally, you guys, ultraviolet voodoo. You know, a silly name. And when you guys move on to college, and please refer to it as the official name, integration by parts, and not voodoo. But from here, most of the kids will, are we doing USUB here? Or are we doing voodoo? So the order in which we do integration is really, there's only three things we learn in this class. It's basic integration, then it's, you know, sometimes it's the special trigs, but that's still considered basic integration. And then U substitution would be the next course of like, I guess, attack if you guys are trying to figure out, well, what do I do here? Try basic integration, then try U sub, and then when both of those fails, you're going to use integration by parts. And those are the three different methodologies that you learn in Calc BC. So integration by parts is, if I were to integrate, it's basically rewriting an integral, just the same way with rewriting for U substitution, we would rewrite an integral. So the integral of, let's say, U and then dV is equal to ultraviolet voodoo is UV minus the integral of V du. So just as a silly way to remember, the ultraviolet part is UV, and then this is voodoo, V du. Okay, so many students find this a lot easier because it's procedural. Yeah, by easier, I mean easier than U substitution. And then also there's a second part that makes it really formulaic for you guys to just, as you're doing these problems, be able to identify, like, you know, U substitution was difficult because you're like, okay, well, what do I let U be equal to? And with practice, that becomes easier. With this one, I'm going to give you guys an acronym that tells you guys what you would let certain variables be equal to. And that acronym is ILATE. So ILATE. You guys can spell that across the top. This acronym stands for all the different types of functions you could possibly get. I stands for inverse trig. So I'm going to spell it going down. Inverse trig. L stands for logs, log functions. A stands for algebraic. And by algebraic, I mean, obviously we had to make an acronym that fit this, but algebraic is like anything very simple, like a polynomial function, like x squared, x cubed. Those are considered algebraic. T and E, if you guys can put like a slash like that here, those are interchangeable. Like it doesn't, and we'll get to problems where I will point this out, but T and E, E can come before T, or T can come before E. And what we do is we read from left to right. T stands for trig. What do you guys think E stands for? What other types of functions do we have? What family of functions starts with E? Yes, and E stands for exponential. So with that, let's go ahead and jump into a problem. Like, all of these are just acronyms right now, and just what is Mrs. Kim saying? Ultraviolet voodoo. So let's look at an example where you would apply voodoo to it. So x e to the x dx. Okay, so let me just walk you guys through. In my mind, I'm looking at this. One, it's not basic integration. So the integrand inside here is the product of two functions. Two, it's not U substitution, because if I let U be equal to x, or x, the inside function here, it's not going to cancel out this x, which is ultimately what a U substitution problem does. And then lastly, I know it's integration by parts or voodoo because I have two different types of classification of families of functions here. X is going to be considered the algebraic, and e to the x is going to be considered the exponential. So when I'm looking up here, this is going to be what you let, and I guess above that, can you guys say let u equal, and then underline that? So what you're going to do is read it from left to right. Whichever comes first as you're reading it from left to right is what you're going to let u be equal to. So similar to U substitution, we're going to rewrite this so that it's in terms of v, like above there, uv. Okay, so we're going to let u be equal to, so we have something that is algebraic. Let me just switch colors to point that out. This is algebraic, and this is exponential. Okay, so we're going to let u be equal to, since a comes before e, we're going to let u be equal to the algebraic function. So in this case, let u be equal to x, And then we're going to also assign another variable. So unlike u substitution, this one has two things you're going to do simultaneously. You're going to let u be equal to x, and the other thing is dv. Okay, we're going to let dv be equal to the rest of the integral. So in this case, this part right here, the exponential. So once you figure out what you're going to let u be equal to, dv is the rest. So in this case, e to the x dx. Okay, and so we're going to do two things again simultaneously. On the left, you guys are going to differentiate, which is take the derivative. And on the right, you guys are going to integrate. Okay, so if I took the derivative, we're going to do it the same way as we did with u substitution. Du is equal to dx. On the right-hand side, with those differentials, dv and dx, what we're going to do is integrate. Okay, so the integral of dv is just, there's a 1 here, so it's just v equals, and then you get the antiderivative of e to the x is just itself, e to the x. And now we write the ultraviolet voodoo formula out. So technically what we're doing is we're taking the original and rewriting it so it's uv minus integral of v du. Okay, so let's, so now what you guys are going to do is kind of view these as a couple of pieces here. Here's u, here's du, here's v, and then that's all you guys need. Okay, so let's find u. U is also equal to x, so we're just kind of resubstituting what the variables are. So u is x. Okay, the next part is v. V is e to the x minus the integral of, here we have v, so we go back to v being e to the x. And then what is du? Well, du actually is dx. And so if you guys look at your equation now, you have that you rewrote this antiderivative right here to be this integral right here to be this expression. And then the next steps would involve you guys integrating this piece. Okay, so we leave, this is already the antiderivative x e to the x. And now we minus the integral of e to the x, which is just itself. And then at the very end, since this is a general antiderivative, general solution, we have the plus c. So this is what, if I were to find the antiderivative of this, this is the solution to it. And we can work backwards, take the derivative of the right-hand side, and we should get back to the integrand inside. Okay, so kind of strange at first. I remember learning it initially and thinking, okay, this is kind of weird. But again, it's for many students, it will become one of the, I think, you guys will eventually enjoy it more than u substitution, or a lot of people like it more than u substitution. So again, we assign two variables, u and dv. So let's go ahead and do u equals dv equals. Can you guys in the chat type out what you think you would let u be equal to according to the acronym above, left to right? What do you guys think u would be equal to? Oh, remember you guys that u is equal to the first function that you guys read, reading it from left to right, like whether it's, so we see we have algebraic and we have a log function, right? So yeah, I see a couple of answers. So what we're gonna do is if L comes before A, L does come before A, then that means that I'm gonna let u be equal to the log function before I let it be equal to algebraic. Okay, so, and you know what, and the nice thing about ultraviolet voodoo is that it self-corrects itself. Okay, so meaning that if you had tried it the other way, it wouldn't have worked out. So in this case, also not basic integration and not u substitution on this either. Okay, so just verify that that makes sense, because if you let u be equal, there is no baby function here anyway, but if you let u be equal to ln of x, for example, on u substitution, 1 over x or its derivative is not within the integrand, so nothing's going to cancel out. So yes, again, I'll repeat that. You let u be equal to the function that appears first when you're reading this acronym from left to right, and in this case, that's the log function. So let's let u be equal to ln of x. dv is going to be equal to everything else. Everything else is x dx. So you want your differential on the side where you're going to integrate. Okay, go ahead and let's find du. Du is the derivative of u is du. Derivative of ln of x is 1 over x dx. And then, so differentiate the left. On the right, integrate. The one with the differential, you guys are going to integrate. So this is always going to be v equals. And the antiderivative of x is x squared over 2. You don't need the plus c. We do the plus c at the very end. Okay, so we're going to rewrite x ln of x, our original integral, using ultraviolet voodoo. So uv is the ultraviolet voodoo. Since u is ln of x and v is x squared over 2, I'm going to put the x squared over 2 first, just so that it's not confused as to being part of the argument of the log. So x squared over 2 times ln of x minus the integral of v du. Okay, so in this case, v is x squared over 2. And then du, we want to be careful here, right? To not forget that it's voodoo, v du. It's all of that right there, 1 over x dx. So times 1 over x dx. Okay, so let's keep going here. So x squared over 2 ln of x minus, I'm just going to stop and say this for, like, when you guys are doing this, you want to make sure if you're doing it correctly, there you should be able to integrate this part. Okay, if you can't integrate it, like we'll see in later problems, they're a little bit more complicated than that. So the x cancels out with one of the x's. So we have here x over 2. You guys can pull out the 1/2 if you guys like. So if I take out the 1/2, I have minus 1/2. And then we're really just integrating x. And the antiderivative of x is x squared over 2. And then at the very end, we're going to do plus c. Okay, so our final solution for this is, if you want to rewrite it, x squared over 2 ln of x minus 1/4 x squared, and then plus the c. Okay, so let's try again. And this, it just takes practice, but let's try something with a little bit more of a process to it. And by the time you guys get to some of these, you'll be like, oh my gosh, I can't believe I'm doing these problems. They're crazy intense, including the last question that we're going to get to. So here, this is going to look very similar to what you guys just did in example 1, but it's slightly different. So can I have you guys type out, what do you guys think you let u be equal to here? What do you guys think you let u be equal to? I'm getting a mix of answers, so just want to make sure this makes sense again. We go back to ILATE. That's what you let u be equal to. We have x squared and e to the x. X squared is algebraic. E to the x is exponential. So when I'm reading this left to right, whichever one comes first when I'm reading left to right is going to be the one that I let u be equal to. So in this case, a comes before e. We're going to let u be equal to x squared. So good job if you guys got that. So let u be equal to x squared. And then dv be equal to e to the x. Okay, oh, sorry, e to the x dx. So again, u be equal to, reading it from left to right, whichever function comes first, and then dv is the rest of it. And again, I'll underline what the rest of it means. Like, sorry, I underlined the wrong thing. E to the x dx is the rest of it. Okay, so then now go ahead and can you guys go ahead and do the first iteration? I'll say it's one iteration, and then I'll say why it's an iteration. So go ahead and try to do the next few steps, and then just cross-check. It's on the board as well. I'm doing it as you guys are doing the problem as well. Just double check your answer. And just if you guys can simply type into the chat yes or no as you're checking your work when you're done. Take a moment to check your answer with what I have so far. You can just, if you guys can type yes or no, you're getting that same exact antiderivative. Okay, thank you for the person who also said that they clarified they found their mistake. Okay, and then anyone want to take a gander at what do you guys notice? Okay, like where do I proceed from here? What do you guys think? Because the next step would be that I'm supposed to, yes, another integration by parts. Okay, so this right here now becomes the methodology for finding that antiderivative is another voodoo. So what we're gonna do is kind of, I'm gonna bracket this. So this bracket part, you guys are gonna perform integration by parts again. And then this one I'm gonna do in that pink. Okay, so okay, so go ahead and do that, you guys. So I'm gonna go ahead and do that in a different color. What would you let U be equal to? What would you let dV be equal to? In this case, U is the algebraic function, just like what we just did in the above iteration, and then see what you guys get for that. Okay, just as you're wrapping that up, what I did was in the pink, I performed the integration by parts again in the brackets, keeping in mind that the first part of integration by parts, the x squared e to the x minus 2, still is there. So this is still part of the problem. I just transferred it down. That's part of our antiderivative. So my final answer will be x squared e to the x minus 2x e to the x. And then now if I complete this problem, I can finally integrate that. And then I get that when I integrate that, it's e to the x. I have a negative out front, but then because that's a bracket, I'm also going to distribute the negative 2. So that's going to eventually yield plus 2 e to the x, and then plus c, because this is a general antiderivative. So this is the solution to x squared e to the x dx. So, and that's not the crazy problem. So the question is, what do you guys think happens if I made that like x cubed or x to the 4th or x to the 5th? What do you think is going to happen? So for, yeah, like if you, exactly. So more and more iterations of doing this, do you have to keep doing voodoo? So luckily for you guys, there's actually a shortcut for all of this. Let me just point out the shortcut to you guys. Notice, first of all, what's happening to your signs, as in positive, negative, as you're going through the first 3 ones. Okay, what's happening to the signs? You guys notice it's like positive, it switches, right? Positive, negative, positive. And we find that as we keep going, that pattern keeps going. Positive, negative, positive, negative. Okay, look at now this term right here, x squared. Okay, how's x squared related to 2x? And then also which then relates to 2. What's happening as you guys are going on x squared, 2x, 2? What's that pattern? Derivative pattern, right? The derivative of x squared is 2x. The derivative of 2x is 2. And then e to the x is harder to see because going in both directions is the same. But if I integrate e to the x, which is inside here, If I integrate e to the x, I get e to the x. If I integrate e to the x, I get e to the x. So this pattern, it can be utilized and summarized in what we call tabular integration. So I'm going to show you guys the same exact problem using tabular integration. You can only, and I think some years I don't make note of this, but you guys can only use this if u is equal to something algebraic. Okay, because the idea is that as you continue the iterations of something algebraic, they're going to simplify out to the very last derivative of 2 is going to be 0. So then there's an end in sight. Otherwise, if you guys use tabular integration, there's not going to be no end in sight, and it doesn't work. Okay, so in our regular voodoo problems, we let u be equal to something and we let dv be equal to something. So in this case, we're going to assign u to be what we had above, which, what do we have? X squared. Okay, and then e to the x. What we're going to do is in between that, or to the left of that, I guess I always put it in between. Maybe it makes more sense to be in front of, no, we'll put it in between. Okay, so the signs switch alternate, okay, positive, negative, positive, negative. So go ahead and put positive, negative, positive, negative, and you just go as far as you need to. On the left-hand side, we know that whatever we let u be equal to, we differentiate. And then on this side, we integrate. So if I differentiate, what I'm going to do is differentiate until I get to 0. Okay, and that should happen when you let u be equal to something algebraic. On the right-hand side, I'm going to integrate. So e to the x, e to the x, e to the x. Okay, so what I'm going to do is highlight the pattern in which you do this. And this is multiplication, but you're going to go ahead and circle. Okay, so x squared times positive times e to the x. And then the next iteration would be this. The next iteration would be this. And then the next iteration would be this. And what we do is we just multiply all 3 things together. A positive times x squared times e to the x is positive x squared e to the x. The next one is going to be 2x times e to the x. So minus 2x e to the x. And then the last one being 2 times positive times e to the x, which is plus 2e to the x. And 0 times, if I had gone one more out, 0 times anything is just 0. So I had stopped there. So plus 0, and then your constant. Okay, so shortcut way. And then if we were to do x cubed, you just do the derivatives of x cubed on the left, and then e to the x on the other side. So I know I don't think I'm going to be able to get to that one particular example. I wanted to do the last example with you guys and come back to the beginning of the next class. We'll make sure that you guys understand tabular, just to make, although I don't feel like most kids have issues with that, but yeah, it's really neat for when we have to do like x to the 4th or x to the 5th. Definitely useful to know. All right, there was 1 year. I'm going to finish off with this problem. I hope I have time here. This is example number 4. 1 year I was teaching Algebra 1 and a kid came in and they're like, Mrs. Kim, can I just practice that crazy question with you before we take this quiz or test? I'm like, sure, go ahead and do it on the wall. And he took up the entire whiteboard. And these are the problems. And then my Algebra 1 kids come in and they're like, oh my God, is that one problem? And I was like, yeah, that's one problem, you guys, when you get to calculus. Okay, so here we have a unique situation. We have exponential and trig. And remember at the very start of this, I said, and I'll come back to it, but I said, put a slash to it, t and e, and whichever one comes first, you guys can pick if you want the u to be equal to exponential or if you want u to be equal to trig. It doesn't matter with this case. Okay, so let's say in my mind, I know that the u is what I want to take the derivative of, and the dv is what I want to integrate. So again, entirely up to you. I'll have one kid come show me one problem and then one way, and then the other kid do another way. We should end up with the same answer. But the reason why I let u be equal to trig, not because of the isolate part of it, but because I know I'm taking the derivative. So if I'm taking a derivative, I'd rather take the differentiate a trig function than integrate. Okay, so take the derivative, and it's easy enough for me to integrate e to the x dx. Okay, sorry, and I stuck the integral in front already. Okay, so let's go ahead and perform an iteration of this. So we go, okay, so du equals cosine of x, differentiate the left, integrate the right, right? So if we integrate the right, we get v e to the x. So I'm going to try to write a little bit smaller here. Okay, so we have the original integral is uv e to the x sine of x minus the integral of v du, so e to the x cosine of x. And I forgot to put the dx at the end of that, but dx. Okay. Problem is similar like the last problem where we recognize, okay, we have exponential and trig, two different functions. We're going to have to do ultraviolet voodoo again. So can you guys go ahead and perform that iteration? Again, I'm going to switch colors just to say that's for this part. Thank you, Min. That's an excellent observation. Min already picked up on the fact that he's like, wait a minute, if you do that again, won't you come up with the same problem again? So just do it and let's see what magical things happen after that. Okay, so go ahead and perform that iteration. But that is an accurate observation. Okay, specifically to Min's observation, does anyone notice something happening as you guys are doing this, as you're completing that iteration? There's something even more specific than what he's stating as is happening here. I guess within the interval, what do you guys notice as you're simplifying this out? Let me just rewrite it as what we have currently. So if you guys can type into the chat that you currently see what I see as your iteration, you guys have what I have so far. And what I'm going to point out next is really the step that I notice if a kid comes to me and it's like, Mrs. Kim, I have a mistake somewhere in this really long problem, negative, 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 negative here. So if I were to distribute that first negative to the bracket inside, I would have that for the second term, specifically this negative to this negative is positive, and then times this negative that I pulled out, ultimately you have three negatives, so it's a minus sign here. Integral of e to the x sine of x dx. Look on the left, look on the right, you guys. What do you notice? Look on the left, look on the right. What do you notice? What we began with, it looks similar to tabular, but what specifically, if you guys look at this expression, isn't it the same thing as this expression right here? Okay, so you kind of like did the whole iteration and then notice you got back to the original. Well, this is something is equal to blah, 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 something of the same thing. So if we have an equation, which ultimately this is, if I add the integral to the other side, then I have one integral of it plus another integral of it, which gives me two of those integrals, or two integral of e to the x sine of x dx. is equal to e to the x sine of x minus e to the x cosine of x. And remember, this cancels out. And how do you guys think you get rid of the 2 in the front? How do you guys think you get rid of the 2? Yes, exactly. It's 2 of something like 2x or 2y. To get rid of that, you divide the whole thing by 2. And then at the very end, just don't forget to do the plus c. So this is your antiderivative. And that happens every time you have something exponential or trig. You just